Okay, we're back. Sorry about that. I have since upgraded to pro status, so now I can have unlimited time. So sorry about the two parts. Anyways, we were in the middle of figuring out how many ions we have. So back to this solute. So sulfate polyatomic is going to stay together, have its charge table E -2. Remember, we have 2 lithium ions. Red. Well, 2 lithium ions here, so we need to include that. So that means 1, 2, 3 ions. So we don't care that this is a different solute than this. They're still going to have the same effect on boiling point, make them higher, and freezing point, make them lower. Okay, so what is freezing point depression? So we're going to take that normal freezing point of a substance and make it lower because we have a dissolved solute. So when a solute is dissolved, it will lower the normal freezing point. The freezing point of that solvent is lowered by 2 factors. 1, concentration. This is that molality. Remember, we did molarity together, but molality on your own. It's just another way of measuring the concentration or strength of a solution. So we have moles of solute over kilograms of solvent. So the higher the molality, the lower the freezing point. So the stronger it is. Something called an electrolyte, which we're going to talk about later, hopefully together. Those are acids, bases, and salts. Hey, you should know what a salt is. Those are those ionic solutions. So things that are salts have a lower freezing point than non-electrolytes. I don't think I can move. Can I move? Hold on a second. Arrow. Oh no. My recording. Where did it go? It's still sharing my screen. Okay. Technological issues. I guess we're going to be stuck with that there. Sorry. So for example, if you have a 2 molal solution, it's going to freeze lower than 1 molal. Why? Because it's more concentrated. For example, salt on the roads. So why do we put salt on the roads? It's not to melt ice. It's to prevent ice from forming. Ice will form at 0 degrees Celsius. And so if the salt, usually like a magnesium chloride or a calcium chloride, when those are put on the roads, it cannot form at 0 degrees Celsius. It might be -10 or -15. If we were together, we'd be making ice cream this week. And if you want, I'm not saying you should because it could be dangerous. You could take a piece of ice and then put some regular table salt over the top. You will feel how cold it is. If you do that, put a paper towel on your hand first because it could really be dangerous. So anyways, that dissolved solute is going to lower the normal freezing point. We can calculate how much lower using this. Oh, wait, we're not there yet. Certain solvents have different effects. Equal amounts of the same solute in different types of solvent. Yeah, so depending on what you're dissolving in. Here we go. We'll go back to that. So here's our formula. The change in the freezing point, delta T sub F, freezing point. These are three things multiplied. I is Van Hoff factor. Hey, remember that? The number of ions. K sub F is a molal freezing point depression constant, which we're going to be able to find. And little m is molality, which you should have been calculating before. So just multiply those 3 things together, and you will find out how much the freezing point will be lowered compared to normal. So here are some, rather common solvents: acetic acid or vinegar, benzene, ethanol, which is an alcohol, and water. This one is found on Honors Reference Table A. So for any calculation, it would be on Honors Reference Table A. Remember, this is not in the Regents, but this will be helpful. Okay, let's do a calculation. How much will the freezing point be lowered if enough salt is dissolved in water to make a 0.50 molal solution? Okay, bear with me here. Delta T sub F equals I times K sub F, that's a K, times little m. Is this formula on the reference table? No, it's not in the Regents. So we need to figure out what all these are to figure out how much lower. Now salt, I believe I meant just NaCl. So before we go any further, how does NaCl dissociate? It dissociates into Na plus and Cl minus. So how many ions are formed? 2. So that's going to go where the I is, 2. What is K sub F? That is the Molal freezing point depression constant. If you aren't on Honors Reference Table, Table A, go there now. Find the Molal freezing point depression constant of water, which is here also, 1.86 degrees Celsius per molal. 1.86. What is the molality? Oh, I told you, 0.50. So then what do? Multiply. Do the math. I'll wait. No, I won't wait. I just hope you do it. So your final answer is 1.86. Your final units, degrees Celsius. Now, what does that mean? That means the normal freezing point of water will be lowered by 1.86 degrees Celsius. So what is the new freezing point? The new freezing point is your normal, which is 0, minus your change. So what is it? Our new freezing point of this solution is negative 1.86 degrees Celsius. Sounds good? But also, if you dissolve a solute, it's going to raise your boiling point. It's pretty much the same concept, just the opposite way. Instead of lowering, we're raising. Normal boiling points are going to be changed by dissolving our solutes. So guess what? It's going to depend, excuse me. It's going to depend on the same stuff. How much there is, higher the molality, higher the boiling point. Things that are electrolytes, those are acids, bases, and salts, are going to have higher boiling points than non-electrolytes. And sorry you can't see that. A 2 molal solution is going to boil at a higher temperature. It's just more extreme. This is a sugar syrup if you're making candies. So the higher the boiling point, the more, the more sugar you put in your solution, the higher the boiling point. So we've got pretty much the same formula, except for now we're talking about boiling point being raised. The change in the boiling point, we still have Van Hoff factor. We have a new constant, the molal boiling point elevation constant, and little m for molality. But same idea. Here are some common solvents. Hey, look, water on Honors Reference Table A if you didn't already see it. I think there were some problems with this question. I didn't include the molality, and I also didn't include what it was. So I would have had to do molality, grams divided by kilograms to get your, no, not even. I would have had to go from grams to moles, and then moles divided by kilograms. We don't need to do this, honestly. It's the same idea as the other one. But let's just say, for example, just for the sake of example, let's just say I'm going to do it, and it says the boiling point has been increased by this. Let's just say not benzene. Sorry, guys. Let's just say it's water. I don't know the normal boiling point of benzene. So anyways, if I have water, the normal boiling point of water is 100 degrees Celsius. If it's going to be increased by 0.51, what is the new boiling point? Well, 100.51 degrees Celsius. You might not think that's a big change, but then again, that might not be very much solute dissolved. So sorry this question was kind of a bust, but hopefully that helps clarify. I think the big takeaway, the big takeaway away from this is the more ions, that means the greater the boiling point, the lower the freezing point. That's called colligative properties. Good luck. Hope this helped. Talk to you soon. And how do I stop it? Keep. Am I done now? I don't think I'm done now.